Let's look at one more. Suppose we have two species, each one preys upon the other. And also, let's say that species 1 reproduces at a rate of 30% per day and species 2 at 120% per day. So not only are we going to now have our two original terms in the equation, but now dx dt is still going to equal negative 1.5y. But also, x is going to reproduce at a rate of 30% per day. So 30% of whatever it currently is going to add to our x population. It's going to increase it at a rate of 30% per day. dy dt is going to equal its original negative 3x, but it reproduces at a rate of 120% per day, which is 1.2 times the size of that population. And here, notice that my y term is first and my x term is second, so I should rewrite it as 0.3x minus 1.5y. And this one's good, that one's negative 3x plus 1.2y. And so this leads me to grab my coefficient matrix, which is 0.3, negative 1.5, negative 3, and 1.2. So now I'm prepared to find the eigenvalues. This is a first order homogeneous constant coefficient linear differential equation that matches that form ax plus by cx plus dy, where a, b, c, and d are all constants. If a, b, c, and d are not all constants, this method won't work. So here I just entered those values into Wolfram alpha. Wolfram alpha recognizes the same inputs that I gave it, so that's good. And I come up with my lambda 1, lambda 2, v1, and v2. So that means that y, my solution, is going to equal k1 e to the lambda 1t, so 2.92 t, times v1, which is negative 0.57 and 1, plus k2 e to the lambda 2t, which is negative 1.42, times v2, which is 0.87 and 1. So again, I'm going to parse this up into the x solution and the y solution. And so again, I'm going to just distribute this into the vector. So I'll have negative 0.57 k1 e to the 2.92t plus k2 e to the negative 1.42t times 0.87. And I'm going to do the same thing for the bottom row. That'll be 1k1 e to the 2.92t plus k2, 1k2, so k2 times 1, e to the negative 1.42t. And now I'm going to plug in my initial conditions again. So x was 500 at time 0, so e to the 0 will be 1, and I'll just have negative 0.57 k1. E to the 0 will be 1, so I'll just have plus 0.87 k2. And same thing down here, but 600 equals 1 k1 e to the 0 plus 1 k2 e to the 0. And now I need to solve this system right here. So to do that, I will plug this into Wolfram alpha to solve this system for me. So here we have the first equation, comma, the second equation. And we end up with a solution of k1 is about 15.28, k2 is about 584.72. So in the first equation, I'm just going to replace k1 and k2 with those values. So here we have 15.28 and 584.72. Same thing for y of t, 15.28 is 1k1, 584.72 is 1k2. And now I'll multiply these coefficients together to get negative 8.71 and 508.71. I can now graph these two equations, and I see something similar, except now notice that species 1 dies off, and that might be explained by the fact that they don't reproduce as rapidly, and population 2 is really thriving. So we see that eventually population 1 becomes extinct at time 0.937, which that's the time that we have to stop this model because it doesn't make sense to be using negative x values and causing the second population to rise because of that. There's a little bit of a rise because the species 2 is thriving, but after time 0.937, it doesn't really make sense what we see there. So after t equals 0.937 days, species 1 is extinct. It does not make sense to consider anything that happens after that time. We could also look at the phase plane for this model to see kind of just what's going on in general. Let's do that real quick. So here we have our original grapher. And here I have those equations input in. It doesn't matter what order you put the terms in, but don't forget those multiplication signs. And for x, I'm going to look at x from about, let's say, 0 to 600. And I'm going to look at, oh, sorry, that's y. Y is going to go from about 0 to 600. Let's make that a little bit higher to 700. And let x go from 0 to, we'll say, 600, since that would cover our initial conditions. It doesn't like to really graph this very well. Let's try something closer to our initial values. And anywhere in here, you can kind of see that the x population is always moving to the left. It is on the fritz. It is going to die off. So let's plot y from 0 to 600. And you can see that that's the population dying off. That's exactly what we saw in our solution curve. And let's plot x from 0 to, I think 500 was our initial condition. So let's go ahead and do that. And there's our curve corresponding to that. And you can see that regardless of what initial condition we pick, there are some where the interchange is actually different. You can see here for this initial condition, it's actually x of t that's dying off and y of t that is thriving. But we can also cause that to switch gears if we reduce the size of y, but we keep the value, initial value of x the same. We can get some pretty cool stuff. And we'll talk about this in another video session where we'll try to understand what's going on here. So in one final video, we'll just go ahead and prove that this solution system theorem works, but we'll go ahead and stop here with our discussion of solving first order systems.